It is 11:11. All right, we might as well start then with who we have here. It's kind of a smaller group today, but that's fine. We can make it more intimate. We can make it more personal for you guys, which is great. So welcome to our workshop number 2. Hope you guys installed everything. If you haven't, keep installing stuff on your computer while I talk up here. So first is some announcements. So we have a new website for one. So if you go over here, here's our really beautiful website, which our webmaster has spent a long time working on. But the important thing, so on our website we have things like the schedule, so you guys can check on here if you don't have access to Slack, what's coming up in the future meetings. And most importantly, we have this team section down here, where if you become a member of the club, you can be featured on our website, and you can add that to your resume, whatever. So if you do want to be featured on the website, we encourage you to become an official member. So now, for membership, we're going to have, or we want one or more of the following per semester. So one option is just come to the meetings and participate in meetings. So you need to come to at least 3 and attend 2/3 of meetings overall to be an official member. Or you can choose to help with a meeting. So if you want to lead a reading group or a workshop, for example, you only have to do one of these in a semester, and then you're a member for the semester. So if you want like a nice, easy way and not have to worry about your membership for the rest of the semester, we encourage you to lead a meeting. Or you can assist us with creating 3 of these meetings. Another option is to commit to a club project. So you come up with an idea, you find some members in this club that you want to collaborate with, and basically you give us bi-weekly updates on how the project is going. And at the same time, we can give you feedback on the project advice. And you can get your project featured on our website, which is another way to boost your portfolio. So from now on, we will be tracking membership attendance. So good job to you guys for being here today. And the URL for today, our attendance is So other announcements is that we're going to have a guest speaker from Stanford coming to give a talk for our club. So Professor Chris Potts, he teaches natural language understanding, so perfect for Amit, right? Yeah. Amit and Shamil. And he's going to be talking about quote-unquote solve natural language tasks. So this means like the current AI capability in natural languages, that's supposed to say fail cases, not tail cases, and opportunities for future innovation within this topic. So he also teaches the CS224U at Stanford. He's quite knowledgeable, and he was my mentor for one of my internships. So this would be a great opportunity for you guys to come. And he's also offered to have dinner with us afterwards. So we just have an opportunity to casually go to dinner around here and get to know him a bit better, maybe network with him, make some connections. So that's going to be October 22nd, 4:30 p.m. to 5:30 p.m. Also in the Student Union, not this room, but just across the hallway, Student Union 4A. So this is going to be first come, first serve. So please sign up. The URL is also in the Slack under announcements. So here I made a posting about it, RSVP on this link here. Just email address, name, and whether you want to join from the beginning. Cool. All right. So agenda for today's workshop is, first we're going to start with a mini deep learning crash course for those of you who might not be familiar with deep learning yet. Then we'll talk about the PyTorch framework that we're going to be using to conduct deep learning. I'll talk about why PyTorch, and then just an overview of how the project works, and then we're going to start getting into some coding. And then future workshops will go in depth of each of the topics that we explore today. So first, a deep learning crash course. So the first question is, where do neural networks come from in the first place? And they're very loosely inspired by brain neurons. Actually, this idea came out in about the 50s, where people thought, like, well, what if we created neurons for our computers? But the similarities do end there. Neural networks today look nothing like the neurons in our brain. And the fundamental unit of a neural network is called the perceptron. So you have a bunch of inputs, then the inputs get multiplied by some weight, and they get summed up. And then if you put many and many of these perceptrons together, you get a neural network, which is a very powerful function. So what is a neural network, and what does it look like in the first place? And also, why is it called deep learning? So a neural network is called deep because there are many layers throughout the network. The way a neural network looks like is that you have an input layer on the left side. It goes through a bunch of transformations in those perceptrons through the hidden layers, and then you have an output layer. And that output layer is a probability of whether the input is belonging to whichever class you want. So the idea is that in the hidden layers, it's able to pick up on intermediate features and become more and more abstract. So, for example, earlier features might start detecting edges, whereas later features might start detecting eyes or faces, and then eventually gets to that abstract class. So just an animated example of what this looks like. First, in the neural network, you have the forward pass. So this is when you pass your input out to your output, and it makes an initial prediction. Now, that initial prediction might be wrong. So if it is wrong, there's some kind of error. And this is an example from 3 Blue 1 Brown, a really nice YouTube video. So once you have the error, you can back propagate that error, which basically means you figure out where that error is coming from within the neural network. You do something where you calculate the gradients of what is producing the error. And there's a lot of math behind this. So we are going to be having a math workshop next week from two of our members, actually. 2 of our members have volunteered to give a math workshop for us, so then we can understand neural networks in depth. So once the errors are backpropagated, yeah, question?
May I know what topic of the math you're going to get involved for the next workshop?
Oh yeah, like topic do you mean like what math areas?
Linear algebra?
Oh yeah, so a little bit of linear algebra, a little bit of multivariable calculus, but it'll be, we'll make it like not difficult, yeah. And then we're also going to cover like different activation functions and things like that. So once the error is backpropagated through the network, and you figure out how each neuron is contributing to that error, then the optimizer of the neural network updates the weights to respond to that error. So here is a little visualization. This is called gradient descent, where you have basically your error and you're trying to go down the gradients to minimize that error. And as it gets better and better, it fits your data better. So this is an example where the model updates are based on the optimizer. And we're going to be talking about that today in the code. Cool. So now we'll go into why we're teaching PyTorch for deep learning. So it turns out that top universities are all teaching PyTorch. Stanford is teaching PyTorch in their official curriculum. I think so is Berkeley. The question is, why are they doing this? So to explain this, let's look at this chart. So on the very left, we have low level. This is kind of like low level languages like assembly. And then we have high level, which is like higher level abstraction, things like Python. So on the very low level, you have TensorFlow, which is a really big, powerful framework for deep learning, and it's probably the most famous framework for deep learning. But whenever you're coding in TensorFlow, it always feels like you're working through this intermediate layer to access this really giant, powerful machine in the back. You have to do this thing where you manage different sessions, and you manage the graph. Things are really not Pythonic in TensorFlow. It feels like that you're trying to code C++ through TensorFlow. And it's kind of not intuitive. On the other hand, at the very high end, you have Keras. Keras is really great for people who just want to get something done with deep learning, but they hide a lot of the things away from you. So you get things like model.fit to train your neural network, just like a single line to do all the training for you. And if you really want to understand what's going on in your neural network, it's not the best way to learn. Now in the middle, you have PyTorch, which is just right for learning because it's very Pythonic, so people who are used to programming in Python can do this very easily, but also it doesn't hide all those small details for you, so you can really understand what's going on. So in summary, PyTorch is quite easy to work with, but it's also good for learning what's happening under the hood. And this transparency allows you to transfer whatever knowledge you learn in PyTorch to other frameworks. Now, for those of you who are very astute, you might have heard that TensorFlow 2.0 came out just this past summer and actually officially came out 2 days ago. So TensorFlow 2.0 combines the best of both worlds with TensorFlow and Keras. So why aren't we teaching TensorFlow 2.0? Well, the reality is that we just haven't had enough time to learn TensorFlow 2.0 yet since it's so new. And also because it's so new, they're still ironing out some bugs and some kinks. So maybe in future semesters, we're going to transfer over to TensorFlow 2.0, but no worries because the concepts you learn in PyTorch will transfer over quite easily. In fact, TensorFlow 2.0 was created as a response to PyTorch because people love PyTorch so much. Cool. So now we'll talk about how PyTorch works. So if you remember in the setup, we asked you to run this command on your command line, conda install PyTorch and Torch Vision. So PyTorch is easy to understand because that's the framework we're using, but what is this Torch Vision thing that we also install? So Torch Vision is this extra package provided by the PyTorch developers to make it easier for you to do computer vision projects. So it has a lot of pre-built implementations for vision. For example, in your data sets, it comes with an object called an image folder, which is able to easily, if you have images separated to different folders per class, it can easily read that in for your neural network. And it also has a bunch of pre-trained convolutional neural network models such as VGG, ResNet, Inception, where you could easily do transfer learning. So it just makes things a lot easier. So let's talk about the anatomy of what a PyTorch project looks like from a very high level. So the first thing you do is you set up your declarations. So these are things like data loaders, your neural network model, your loss/error function, optimizers. And then second, you take all these things that you set up and bring it into your train loop. So in your train loop, you iterate over your data. So you do the forward pass through your network in that animation you saw earlier. Then you calculate the loss or error, and you back propagate that error, and you update your model using the optimizer. And this goes over and over and over again. So don't worry if you don't understand all the details of this yet. We're going to show it to you today in the code. So all of this stuff can be done with pure PyTorch. However, Torch Vision, as I mentioned before, offers you some pre-built things in terms of data loaders and models. It just makes it a little faster and easier to get started. Cool. So with that, let's get into the coding. And Jason Doe is going to be teaching the coding today.
Hi.
So to get started, go over to our GitHub, github.com/sjsumlclub. And the project we're doing today is Anatomy PyTorch project. So go ahead and open this. Click the clone or download button. And then open up your terminal. It's going to clone that. And if you're using Conda, which we recommended, you're going to do Conda activate whatever environment you use to install your dependencies. And then you can type Jupyter Notebook right here.
Or we can just download the folder.
Yeah, you can also download it instead of using Git to clone it.
Show them how to download that.
Oh yeah. So if you just want to download it without cloning, you can just do download zip, and it's the same thing. So let's make sure everyone can get to this screen. If you need help, just raise your hand.
So you go here.
What are you trying to
Oh no, I don't think to put them.
do? In browser,
Okay.
go to github.com/ is ML SJSU? SJSU ML?
SJSU
ML Club.
Yeah,
SJSU
great
ML
questions.
Club. ML.
I'm gonna split screen this stuff. Let's see. Here we go.
Have you installed PyTorch and other packages?
Yeah, I'm doing it right now.
Okay, no worries.
This one,
And
it's just CML.
Yeah. Okay, there we go. You just go
So it's the
If you've gotten to this screen, just give a thumbs up.
and go close or download.
Let me come around and help you out.
Oh, we have to. Okay, yeah, sure. So after you install PyTorch, how do you install Jupyter? Oh boy. Conda.
Conda, yeah.
Okay.
I think I have Anaconda, so is it?
Yes,
Okay.
it's already built in.
Alright.
So, did you create an environment?
Mm-hmm.
Okay. So are you in your environment right now?
Yeah. I just downloaded the package.
Okay, sure. So you just have your desktop, right?
Jupyter GUI. You don't have to be in a directory per se.
So you have all your files here. You just
How did you
open this
open it?
Jupyter. So you can type
Yeah, I went
Jupyter
to
notebook.
a folder.
And you have, yep,
Yeah, PyTorch and great.
so you're actually using, so just go over to the,
With Y.
Everything is having access to this.
J-U-P-Y,
Like,
yeah.
it's in the same folder, so it should be fine.
It's E-R.
oh,
Notebook.
no,
Yeah.
that's fine.
No, with a slash. With a space, sorry.
And when you're ready,
Hit enter.
when you're ready, go ahead and open up the,
You should be
this
able
one,
to
the
open
top one, not the answers one.
in your browser. Okay, cool. See, that's the file. So you don't need to just open the workshop one.
Yeah. So if you want to make sure everything's working, just add a cell on top and just say imports torch,
Yeah, just
and that should
type that
work.
to make sure your package is working.
Andrew, do you want to adjust the camera? Because
Yeah.
I gotta be next.
I'm screen recording here, so
Okay. Oh, do you want to do it?
if you don't mind.
Okay, that's even
I'm
better.
already screen recording on this one.
Okay.
So you can open a cell and try to do that with import torch.
I moved your phone, so you might have to
Oh,
adjust.
that's fine.
If it shows error, it means that you then shift enter. Shift enter means run the cell.
Does anyone need
Oh,
help?
you're good.
Everyone good?
Okay, just click on
Great. Wait for everyone to do it. Steve. Made just in time, just starting.
We're here for like 15 minutes.
Alright.
Class.
Just do
What are you guys working on?
PyTorch.
Wow. Nice.
sorry to
Neato.
not a little bit of the back.
What's it doing?
And then just
Dude, I love your
work
PowerPoint.
and shift enter.
Pure PowerPoint. Oh, thanks.
Yes, just wait.
Is that the follow along thing?
So you don't block anything.
What?
So you don't block anything.
Alright, we're good.
Good? Everyone ready to move on? Cool. Great. Take it away, Jason.
All right. So, hi guys. I'm Jason, treasurer of the club, and here I'm going to lead you through this workshop. Okay. Yeah. If you were here for like our first official meeting, we touched on this project like about quarter of the way, quarter to halfway, but we also kind of rushed it. So we're gonna go back and go over this whole thing more in depth. So now you can feel free to ask more questions. We're not as rushed, so we can spend more time answering the things you want to know. Okay, so let's get started. If you've downloaded the zip file or clone the database, clone the GitHub, then you should have our data folder in the correct directory. To verify this, you can type this command, /try/chihuahua.
I'm sure this
Oh, whoops.
Right, do you just do ls data?
Ls data.
Oh yeah, I think you do have to download the data.
Oh, you didn't?
Oh yeah, so download the data from the link.
Well, all right, let's try and do that.
Yeah.
Okay, so you got to download the data from this link.
Downloads the data.
Oh, here it goes.
Top right.
Do we put it in like
You gotta-
main folder?
You have to put it in the directory of your whatever directory your Jupyter notebook is installed in.
Do we put it in the same directory as like the other two notebooks?
Yeah, the same directory as the notebook.
I'm just gonna do that. What do we call it? Oh yeah, workshop, anatomy, PyTorch project. Just gonna open up that folder, put it in there,
You have to unzip it.
unzip it. Yeah. Extract here. Blah blah blah. And it should be just a data folder.
Yeah.
Yeah. Right.
Okay.
Let's do it.
All right, yeah, so yeah, download the data from this link and put it in the same folder as your two Jupyter workbooks. And then you can run this command. There we go. So what this command does is, it's just basic bash command. It lists all of the files inside this particular directory. And as you can see, these are all image files, JPEGs. This is the data that we're working with. And I actually, when I was doing this project, I had to manually search on Google for all these pictures of chihuahuas. If you're on Windows, you will probably have to run this command. Train if ls doesn't work for you. Yeah.
Jason, can you make it a little bigger? It's hard to see.
Is this good?
Okay. Yeah, so either one of the commands. If the first one doesn't work, then the second one should work. Everyone good?
What'd you say?
Second one is also not good.
Oh, if you're on Mac, then it should. Oh wait, it's also not working. Did you download the data?
Yeah.
Okay, huh.
You can try restarting your Jupyter notebook and that might fix it.
Yeah, it's just import Torch. So this one, yeah, just import Torch.
Oh, use backslashes instead of forward slashes. Wait, I Jason, for Windows, I have to use backslashes.
Oh yeah. Backslashes. My
There you
bad.
go. All right.
Okay, so yeah. Anyways, this is just like a verification step. It's not like particularly necessary for the project itself. So if it doesn't run, it's fine. Just make sure that the folder is actually in the correct place. Next, we have to import the image class from PIL. This is a Python image library. So PIL import image. Okay. So this imports all the stuff under there. And then now we can actually open the image file and see what it looks like. So x equals image dot open, and then you have to type in the directory for one of the images. So data /train /chihuahua /10. Okay. And now we can take a look at it. So if you run this, you should get an image of Chihuahua, a Chihuahua. So here's one. This is the 10. This is the image labeled 10.jpg.
And if you guys need us to slow down, please speak up. Else we're not gonna know. So just say slow down, please. That's
Yeah.
totally fine.
What we are doing, what's the goal we are doing?
Okay, then yeah. So let's go over the overall project. So this was actually one of my semester projects for my graduate level machine learning classes. And my project was to classify the difference between chihuahuas and muffins. If you've seen that internet meme, chihuahuas and muffins kind of look similar in certain scenarios. So let's pull that up.
Sorry to interrupt. Can you go back to the
Okay.
a few lines above?
Yeah.
Yeah,
So-
how you can retrieve your data.
Yeah.
Make sure you are able to.
Like I
retrieve
said,
all
this
the data.
is not a vital line of code for the actual project. This is just a verification step to make sure that you install the data folder in the right place.
For those who haven't seen the meme, we can also show them.
Yeah.
Wow, there's another control T.
Right. Let's explore my motivation for this project. Actually,
No, not LS. LS only. So those just do the IR.
there we go.
Because people
Yeah.
are using different OS.
So as you can see, chihuahuas and muffins do certainly look very similar in certain cases. And I tried to train a classifier to help humans decipher between chihuahuas and muffins. This is indeed a valid machine learning project, and I got graded on it.
Good question.
Yes.
Are we gonna need a GPU to train this data set, or for now will CPU be sufficient?
So yeah, this is actually comes up a bit later, but in general, you don't really need the GPU. It's just
For this
nice
project.
to have. Yeah.
For this
For this project, you don't need it. And
Yes. Or maybe you can change the limit. You know, it's a little bit.
if we go into the muffin side, I think 150 is more. Nope, not 150. Right, 150 is too much. I think 99. There we go. Yeah. So in the muffin folder, we have also pictures of muffins. This one is muffin number 99. Yeah. All right. So yeah. Once again, these are all. This is just verification at the moment, so you don't really need to you don't particularly need to run this line of code exactly. You just need to import the image library, and you should be done. So yeah, this is what various machine learning data folders might look like. You would have it in your root or something, and then you can classify your folder as dog, and then put all your dog pictures in there. And you classify all your cats, and put all your cat pictures inside of this cat folder. This helps the classifier. This gives the classifier like the correct labels, right? Because they need like an answer to compare their answer to. So if you don't tell them the right answer, they can never learn, right? Just like if you were doing homework by yourself and you didn't have like a teacher giving you the correct answers, you'd probably think 1 + 1 = 3 or something and spend your entire life never figuring that out. So same thing here. You need to correct your image classifier. Okay? Okay, we need to do more imports. We have to import image folder this time. And this is from Torch Vision. So just run that and it should work. Good? Okay. And once more, we need to import another thing. Torch Vision. Okay. So this line imports the transform library. And what transforms are is that when you are pulling a bunch of different data, let's say from Google, right? They're not always going to be exactly the same size. And that might be enough to throw your classifier off. Because let's say you have a really big chihuahua and then a really small chihuahua. It might confuse your classifier, right? What transforms do is you can try and regulate the size of your image. For example, here we're going to do a transforms.resize to 224 by 224. That'll be 224 pixels by 224 pixels. So it's basically a square in width and height. Right?
How many people are following along up to this point already? How many people are behind a little bit? Okay,
You
just
just got it.
Is anyone else behind?
So if you want me to go back a few things, go back to some previous code, all we've done so far is just import stuff, really. So import the image, import the image folder, stuff like that. If you're really, really behind and you would like to go at your own pace, feel free to open the answers file. It has all the code already written in there, so then you can like just quickly catch up if I go too far ahead. Yeah. Okay. So let's write the transform function. This one is a bit of a lengthy line of code. Forms equal transpose. Oops. Okay, so this is a really long line of code. All it does is it takes it composes a transform with the resize function that changes it to 224 pixels by 224 pixels, and also turns each of the images to a tensor. So tensor is just a way of representing each image in an easier way for the computers to process. Okay, and then we run this, and it will show us what the transform function looks like in Python. So here we have the resize, 224 by 224, and we also have the 2tensor, and they're all packaged in one little structure, and then the machine learning classifier will take that and run it on the images. Make sense? Any questions? All right, well, we're gonna move on a little bit. We're gonna instantiate the actual image folder object. So my data set equals image folder. Train. Okay, so now we're linking the transforms to the training data set right now. So this is now a structure wrapping all this stuff. Let's see what that looks like. Oops. My data sets. Yeah. So here in the image folder, the data training image folder, we have number of data points 120, which means there are 120 total images in the training data set. So overall in this project, I have sourced 150 images of chihuahuas and muffins from Google. Yeah, and put them inside my data folder. What I've done ahead of time is I've split the data into 120 pictures for training and 30 pictures for testing. So 150 in total. So why 120? Well, 120 is 80% of the entire, and it's traditional to split your training and testing set into 80% training and 20% testing, somewhere along those numbers. Okay? So why do we do that? Well, basically, we want to have a lot of data for our computer to train itself on. We want it to be able to learn a lot before we actually test it. But we also want a good size amount to test our computer to make sure that it actually can get stuff done, right? So we don't want to put everything in the training set, and we also don't want to put everything in the testing set. So this 80-20 split is usually a good compromise. Somewhere along these values, you could do like 70-30, 90-10 if you have a particularly large amount of data. Yeah, but generally around this range is a good recommended split for your training and testing. Everyone clear on that? Yeah?
Sorry, I couldn't really get why you initiate the image folder object.
So this one?
Yeah.
Yeah, so this is, this image folder object takes in the directory of your training folder, and then it links it to the transforms that we just defined, meaning that when this whole thing runs, it will transform all the images inside this folder,
Oh, I got it.
training folder, according to what we wrote here, resize and totensor.
Oh, I see.
Yeah. Okay, everything good? Okay. So this dataset object is treated like an index, or it has like an index. So we can look inside, let's say, what the second item in the thing looks like. This is a tensor. Okay. So a tensor is just like a big matrix with different values. There are 3 different values. And it's just like a whole bunch of math to try and map each pixel, basically. The tensor has, if I recall correctly, it has 3 matrices, each one for RGB. So this is, let's say, red, right? Red color. This is for the green color. And this is for the blue color, right? So let's say the very first pixel has whatever this means in tensor speak of red. And this pixel has whatever this number means in tensor speak for blue, and this has whatever this number is in tensor speak for, whoops, this one's green and this one's blue, right? So we don't actually know like what these numbers mean, but the computer does, and that's the important part. Yes?
Would you mind show us the output?
Output of?
Of the tensor. What's the tensor transfer?
So this is the tensor itself.
I think she's asking, what does it represent?
So this tensor is supposed to represent a single image. So this is my data set 2, right? Which is basically the third picture inside our data set. So remember, it counts by 0. So 0, 1, 2. This is the third image. Okay?
So you
And
remember
this
how an image is basically pixel values, right? With RGB layers. So this is a tensor with RGB, I guess, depth, and then it has a height, a width, and a height. And then each value here between 0 and 1 corresponds to the pixel intensity between 0 and 255.
Yeah. But remember, this is just for the computer to read, basically. We can't really make heads nor tails out of it. If you notice at the very end, there's this lone 0 here. And this lone 0 is pretty important. This is the actual label that's given to the image. So our labels, the choices are Chihuahua and Muffin, right? So our computer's converted Chihuahua to the value 0. And you know, it stands to say that obviously the value of 1 would represent Muffin, right? So if your project had, let's say, many different classes, let's say 3 classes, then the value 2 would be assigned to your 3rd class, the value 3 would be assigned to your 4th class, and so on and so on. But right now we're just dealing with 2 classes, 0 for Chihuahua, 1 for Muffin, and it's right here. Okay. Now we have to do a bit more importing from torch.utils data import data zipper. Okay. So we're importing the data loader library. This will help us load the data into our actual classifying code. Right? So we can't easily pass in the data folder to our code. So we have Torch Vision supply a data loader to help us do that. And then my data loader equals data loader. Here we're just instantiating it with my data set. And then we will discuss this these arguments when I'm done. Oops. Workers equal 4. Shuffle equals T. Blue. what did I just do? Well, like I said, I'm instantiating the data loader object on my data set, right? And this batch size, what is this? Well, basically, when we run our training program, or training code on it, we could run each image individually, one at a time. But that means we'd have to do this basically 150 times for each image, which isn't very efficient. And especially if you have a project that has like 10 million images, you don't really want to do it one at a time, right? So we have this batch number, which means, hey, I want to process 16 images at a time. This will help us run things a bit faster. And if you have a powerful enough GPU or CPU, you can handle this amount and possibly even larger. This num workers is, well, it just like specifies how many things you want to run in parallel. So say there are 4 workers working in parallel, and each of them takes in 16 images per batch. And this just helps speed up the work pretty quickly.
So basically, the number of workers is telling how many threads on the CPU to spawn to do all those transformations and loading your images, so it's faster for the GPU.
And then this last one, shuffle equals true. Basically, we want to be able to randomize the set of images we run each time. So let's say inside the training folder, every time this runs, it shuffles the images in a varying order to make sure we don't like train it like too well on this specific list of images that were arranged. So yeah, we don't want to do that. That might mess up our classifier. And then we run this code. Wait.
Batch size.
Whoops.
Underscore.
Yeah. There we go. Batch size. Okay, so this is what this whole thing looks like. We have our dataset image folder. Remember, 120 data points. It's located in data.train. This is the transform applied to each image. And then we have number of workers, and then we have all these various other arguments. Don't really need to worry about it. Okay, what's in our data loader? Okay, so, ooh, I forgot to write the one that makes more sense. So this is a very roundabout way of basically,
Data floater.
yeah, we're basically taking, whoops, data floater. Yeah. This is basically a roundabout way of getting this variable data to have the first element inside data loader. And then tensors labels equals data. And the variable will have this tuple that has, remember, you see the tensors and the label. Label was the 0 at the very end. And then we're going to check this. Oops. Tensors dot shape. We're going to check what they look like. Labels dot shape.
Labels dot shape. You put labels common shape.
Oh, whoops. Max. All right, here we go. Yes, so you see the tensor looks like this. 16, 3, 224, 224. So let's take a little pop quiz. Who can tell me what this number might represent? Anyone? Batch size, right? Remember we specified the batch size of 16. What about this number?
Number of pixels or colors.
RGB, right? RGB, 3 colors. What are these two? Should be easy. Size of the image, right? Yes. All right, what about here in the labels? What does this number represent? What was it? Number of pictures, yeah. It's also specifically, since this is the labels variable, this is the number of labels, remember? So Chihuahua or Muffin, there are 16 values of them. Of course, they're translated to zeros and ones. So there's going to be 16 zeros or ones in there. And yeah, good job. Any questions? Okay. We have to do more importing. Import Torch Vision dot models.
I had a question.
Yeah.
So, can you go back to before the data loader?
Before the data loader.
So, there was this tensor in my data set.
This one?
Yeah, so, the last point is a 0 or a 1.
Yes.
So, we haven't really, like, I don't think we have gone through a step where we are training or something, so how do they know it's a
Yeah,
zero?
how does the computer know that this is a 0, in this case a chihuahua? Well, if you look at the very, very beginning, I've already helpfully done that for you by specifying the folder labeled muffin or chihuahua, right? So all the images inside that folder, chihuahua or muffin, are chihuahuas. Well, they should be, if I'm a good
So
data
just
filter.
based on the folder, it's
Yeah.
changed to the.
Yeah, based on the folder that you label, and the computer will pick up that, okay, this is the first folder, 0th folder, this should be class 0, and this is the second folder, muffin, this should be class 1. And of course, when you do this, you have to make sure that every image that you put inside that folder, it has to be a chihuahua. If you mess up, then you're gonna mess up your entire project, okay?
So could you go to the data loader?
Yeah, data loader.
Can you explain again what the batch size is?
Yeah, batch size. So we have 120 images total in our training set. Okay, if we were to run that one at a time, one image at a time, it might take a while. And it will take especially a long time if we were walking around a project that had, let's say, 1,000 images, 1 million images. So we don't want to do it one at a time. We want to be more efficient. We want to do it 16 at a time, 16 images at once. And we can go even higher if necessary, and we have good enough specs.
And what about the shuffle?
Shuffle. So in my data folder, I have a specific ordering of the images, right? So I ordered them by their number. So it's 1, 2, 3, 4, 5, image 1, 2, 3, 4, 5, and so on. If we set this shuffle to false, it will take that order the same every time it runs. And that might be too convenient for our training. It might make it too easy, right? We want to be able to shuffle the images around so it's not too good at training on that specific order, 1, 2, 3, 4, 5. Maybe we want it to be like 5, 3, 4, 2, 1. Or
So it randomly pick up the.
yeah, randomly takes 16 images from the folder and then does that through every time.
I can expand that answer a bit. So the batch size of 16, remember that we're putting these images on the GPU. Now, the power of the GPU comes from being able to run multiple things in parallel. If you just put one thing on the GPU, then you're not running anything in parallel, right? So that's why we have a batch size. And then the reason why we shuffle is because the neural networks are so good that if we don't shuffle it, it might just learn that order of going in order rather than based on the input.
Exactly. Right. So we do want to challenge our model a little bit. We don't want to make it too easy, otherwise our model is too simple. Okay. So if you guys were here in our last meeting, we did a little discussion on AlexNet, and we're going to actually implement it right now. So my net equals models dot alex.
Yeah.
Sorry, this is not my computer, as you may know. Yeah. My net parameters. Okay, so yeah, AlexNet, right? It's the model that we discussed in our last workshop. It looks like this. Yeah, don't worry if you don't really understand what it looks like. It just looks like this.
I think most people here were not at our reading discussion, so can explain a little bit about AlexNet really quick. AlexNet is a convolutional neural network, and it's really good at taking images. So you can see on the leftmost side, it looks like an image. And then the convolutional layers basically compress that image into smaller and smaller layers until you come out to like your final layer for your classes. AlexNet was really revolutionary because it was the first neural network that really did well on the ImageNet challenge, which is a really difficult challenge with millions and millions of images and thousands of classes. And this improved the top accuracy by like a significant amount.
Yeah. And we have, it's in this Torch Vision model library, so we can just take it. So what we're basically doing is we're borrowing the work that these guys have done to create AlexNet and applying it to our project here. So, we computer scientists, we're kind of lazy. We don't like to reinvent the wheel, right? So these guys have been nice enough to provide us with this nice AlexNet model. We're just going to take it and use it for our own purposes. So this is what it looks like. If you look really closely, you can see a list of these, let's say, functions. 1, 2, 3, there are 12, right? And if you count here, actually, this is 1, 2, doesn't match up, Alex? Or Andrew?
Oh, the diagram is a summary.
Oh, yeah.
So there's like intermediate layers there, like ReLU.
Right.
So the ReLUs are taken out and not shown in the diagram.
Yeah, so let's see, 1, 2,
Dropout as well.
3, 4, 5. Yeah, there's some that are not shown, but the more important layers sort of match up with these lines of code here. So we don't really, well, they should be in order. So this one should be like 1, this one should be like 3 or something. But yeah. All right, now we're just gonna do a really quick test. We're gonna pass a single image through this model and see what pops out. Images equals next iter my data loader. Okay.
Any questions so far?
So we are taking the stuff from our images. We're setting images equal to the next image in an iterator of our data loader. So we just take the next image. And then we're going to set it equal to, by passing the image through the network, or the net, AlexNet. And then we're going to check what it looks like, the shape. OK, so out pops up this thingy, another pop quiz. Well, you probably won't get the second question, but what is this number again? Batch size. Now, this is a challenge. If you were in the discussion, you might know this, but what do you think this number might represent? Number of classes, this guy got it. Yeah, so AlexNet is not as specific as our project, right? The people who designed AlexNet, of course, didn't design it to classify between chihuahuas and muffins, right? That would be too convenient. They designed it to classify between 1,000 different classes, to 1,000 different labels. So there are a few labels, let's say, I don't know, like square, animal, do you know any?
Boat.
Trees. Yeah, so if our image is any one of those, we would expect that the tag would be flipped on one of those labels, right? And so let's say if there was a tag in here, a label in here that was like dog, right? We'd expect that one to be flipped, right? But if there was a label in here that was like cat, we'd expect that to be not flipped. But of course, with 1,000 labels, we don't need all that information, right? We just want to know, is this a chihuahua or is this a muffin? So what we're going to do is we're going to take all the work that AlexNet did for us and expand on it to get the answer that we actually want.
So does AlexNet output classification, or does it give you like probabilities for each class?
Scroll up. I believe it's just the raw output. No, scroll up to here. Yeah, so the last layer here is just a linear layer. It's not converting it into a probability layer, which would be a softmax layer.
Okay.
Yeah, so it's just the raw output.
Okay, gotcha.
Yeah.
Good question.
So we're going to do more importing. Import torch. So we're taking torch.nn, which is the neural network library. And we're going to take stuff from it. Oops. pretty long line. Let me see if I can.
I think you can press enter after the parenthesis. And
There we go.
yeah.
And then, parameters. Okay. So, let's take a look at this code and try and deconstruct it. We're taking this classifier thing, right? And we're borrowing this sequential neural network or layer, and we're so my net classifier is all the AlexNet stuff, right? This outputs the 1,000 labels, and then this is a linear layer, which takes in 1,000 labels and only outputs 2 labels. Remember, we are working with chihuahuas and muffins. It's only 2 classes, right? We want to take this 1,000 classes and output an answer based only on 2 classes. Right? We're reducing the 1,000 to 2. So if we run this, this is all the AlexNet stuff, right? Including this, right? And if you see here, we have this sequential wrapper that wraps it up and then adds this linear layer that we've defined that takes in 1,000 and outputs 2, right? So basically, we're just reducing the output of AlexNet into the 2 labels that we really care about. Any questions?
Can I go up?
Yeah, sorry. Yeah, it's a long line of code.
Question? What is dropout? So I think we did not get the dropout in our reading discussion last week. So dropout is a way to prevent something called overfitting. Overfitting means that your model learns things it's not supposed to learn, like noise in the data, and it gets too close to that. So dropout means that you randomly take a set of neurons or connections and you just set that to 0 randomly through every iteration. And this basically forces the neural network to develop a better variety of paths through the net so it becomes more general. So they used dropout here because they found that it improved accuracy for them.
All right, everyone.
Got question?
Okay.
So how does it know how many, like, for that neural net, how many layers to use?
Yeah, so here we
How many
specify
nodes per layers?
the 1,000 layers that the AlexNet.
Well,
Input.
like that's for the input, right?
Mm-hmm.
So that means like the input is 1,000 nodes, but like, how does it know like how many layers to use for the neural net?
It just does
Like,
this.
How many hidden layers and stuff?
This is just a single layer, is that right?
Is your question like, how do
It's a
we?
single layer.
Is your question how do we design it, or how's it shown in the code?
Like, so the NN is like a neural network, the sequential neural network, right?
Sequential, yeah, it sticks a bunch of layers together, basically. So every single one of those lines is a neural network layer.
Oh, okay, gotcha.
And sequential just means run the input through them sequentially.
Okay.
And as you can see, this
Okay,
is
that makes
the last one that we added, right?
Mm-hmm. So in the last one, we had what was there previously, and then we say also run this extra layer that we added, which converts 1,000 to 2.
Yeah, okay.
Good question.
And what is that bias equals true?
What is the bias equals to?
So in your neural net, you sum up the weights, and then you have the option to add a bias to that weight, which is also a learnable parameter. The neural network will also update this bias. But it just says that we do want to add a bias there.
All right. So everyone here? Okay, let's do a quick test to make sure everything works. Choose.
19 minutes left.
Oh. Well, we're almost done. Well, okay. Actually, let's try and hurry it up. Okay, we're gonna run this, and look at that. It's taken our 16 batch size and reduced it to only 2. So that's what we want, right? 2 classes. Cool. All right. Now we have to define our loss function. Like Andrew was discussing earlier, this is the function that tells us how badly our classifier is doing, right? It generates an error, and then it will try and quantify this error using this function. So we define it as such. And cross entropy loss. Okay. So this is a common loss function from our neural network library. This is one that's pretty commonly used. And then it spits a number out to determine how badly, the error rate, right? How badly we're doing. So that's the general way of describing it. If we had more time, I'd explain it more in depth.
We'll also talk more about the math behind cross entropy loss in the next workshop.
Yeah. Okay. Ooh. Yeah, this isn't part of the code. This is just like the GIFs and stuff. This is the code, right? So criterion, my loss. So this basically is the number, the error number it's spit out, basically, right? Yeah, and we can't really make sense of this. This isn't like a percentage or anything. This is just a raw number. So humans aren't meant to look at this and derive meaning from it, but the computer can. That's the important part. So these are some GIFs that sort of describe how an optimizer looks. Basically, here they're trying to reach the star, right? And these are various optimizer functions. And each of these circles, one of them reaches the star first. I can't really tell which from the image, but yeah. So this is just comparing performances of different optimizers. But let's just quickly get our optimizer up and running. So optimizer equal optim. Oh wait, I didn't import it actually. I need to import it. Import torch.optim as optim. So PyTorch has provided us with an optimizer library. We're gonna borrow one of them. Equals std my net dot parameters are equal 0.001. Yeah. Okay. So this optimizer function that we're using is, I forgot what the S stands for. Stochastic gradient descent. Yes. We're taking this from the optimizer library and then we're applying it to our network with a learning rate of 0.1%. And that's just, why do we use 0.1%? It's just
a
standard,
common number that people
common
start
number.
with, 0.001, 0.0001.
Yeah. So this is just basically we're borrowing the optimizer from here.
The learning rate affects how fast your neural network adapts to that error. So a bigger number would be that it'll change the weights faster, but that can also mean that it might like bounce out.
Mm-hmm. All right, we're at the final step, our training loop, which is the most exciting part. We got to import torch. I think we did it earlier, but we're just going to do it again. Wrong one. And here we're specifying the device that Torch is going to use. If Torch is available, else CPU. Net to device. Okay, so what we were doing here is this funny word CUDA is basically used to refer to your NVIDIA GPU if you have it, right? It's just what NVIDIA likes to use. And we're saying if we have this NVIDIA CUDA, use it, else we can just use our CPU, right?
You spelled device wrong.
Oh, did we? Oh,
The first one.
shoot. All right, and then we're sending our network to the device. Oops. Yes. So get this code. How much time do I have left?
14.
Okay, perfect. Okay. Yeah.
We're almost there.
Almost there. This is the final and most exciting step. And it's the longest step, right? We have to write a lot of code. So let's try and get through this. First, we're gonna import this TQDM library. But then you already used TQDM.
You just take that.
Okay. All right. Well,
I'll do the TQDM later.
Okay. Very well. Num epochs equals, should we just set it to 5 for now? Sure. Yeah. Okay, so epochs. What is an epoch? Well, basically, it might not be enough to run through all our images once, right? Epochs refers to the number of times we want to run through all our images, the number of times, right? So this means we're going to train it on the training set, the entire training set 5 times. Yeah. The more epochs you have, it might get even better, but it also might get worse if you have too many epochs. So it's basically an art to figure out the correct or the best number to use. This, we're just creating a little accuracies array to keep track of the accuracies we get per epoch. And then we have to loop over the epoch for epoch in, range num epochs. Desk.
Oh, you're just here.
Hmm?
That's the TQDM.
Oh, is it? Okay.
I just do this. Get that. Oops.
Ah, okay. All right. All right. So this is just the for loop, right? We have to track our accuracy.
Why does it get worse with more epochs? Is that because it overfits?
Yes.
Yeah. Correct. This epoch equals 0. This is to track our accuracy. Then we have to loop over our data loader for data labels. My data loader.
I notice you guys are frowning in the back. Is it because it's hard to see, or your question? Okay.
And this
Complex
this
stuff.
part is for the TQDM as well, right? Leave it as well.
Just
Yeah.
do that, and then colon.
All right. Ooh.
There you
Put it in.
go. Mhm.
Okay.
Okay.
Data dot to device labels dot to device. Okay. So here we're sending it to device again. Pass the data through the model. Puts equals my net. So we did do this code before on a single input, but here we're putting it in a loop, right? So we're doing it through every input this time. And then calculate the loss. So look at this, right? The outputs is basically the label our classifier is giving to each image. So it's gonna pick Chihuahua or Muffin. And then we have the correct answers here, the labels, right? Chihuahua or Muffin. It's gonna compare the two and see how badly it's done. Zero grad optimizer. 0 grad. So 0 grade, run our optimizer on the result.
The 0 grad just clears out the past gradients from previous iterations. So we want to re-update that gradient every single iteration.
Yeah, and here we run the backward pass via our loss.
That automatically does back propagation from your error throughout your network.
And then we're gonna step our optimizer. Basically runs it.
And then that's the wait update, optimizer.step.
Okay. Then I'm gonna do this very long line of code. Well, it's not that long actually. Creds equals torch dot max outputs.
So the class that it predicts is going to be
the index with the highest value in that index. So either Chihuahua or Muffin. If Muffin is greater, then that's the prediction. And I'm just tracking how many we got right.
Yeah. So this is just a simple, increase function. If your prediction matches the label data, then you increment the correct this epoch by 1. Okay. Accuracy, this epoch. Okay, so this is just getting the accuracy percentage, right? Dividing the total correct this epoch by the amount of images we have. And then we can print it. Then we're going to append this to our list that we made earlier to keep track of it. Epoch. Okay, so yeah, this was a lot of code. Did everyone get it? If not, you can look at the answers file. It should have everything in there.
You can leave it up for a little bit.
Yeah. Okay. And then I'm just gonna run it. Whoops. Oh yeah. So I ran it, which means it's currently doing the training loop.
Yeah.
So 5 times. So as you can see here, it's got the asterisk. This may take a while, and if you increase the epochs, it will take even longer. So
we want to have some kind of progress bar so we can see how well it's doing. So we're going to import this really handy library called TQDM.
Yeah, so Python has this handy library. So right now, looking at it, we can't really tell anything is happening, right? There's some output here, right? So this outputs every time per epoch, right? So we're on the 5th run right now. It's running, and then eventually you'll pop it out, right? There it is. And then we're done. So that wasn't very exciting. We want to add some spice to it. So we're using this TQDM library. TQDM, and then we're going to see what it does.
So for both of our for loops, we're going to wrap it in a little TQDM function.
Okay. For data, labels and TQDM. Whoops. My data loader. Okay, so yeah, we've wrapped all of our for loops in the TQDM library. That's the only place where we have to use the function. And then we run it, and then we'll see the difference in what pops out. So run it, and look at this. We have a nice loading bar. Cool, right? So now we can actually see the batches being run through. As you can see, there are 8 batches. So why is that? Well, there are 120 images in the training library. If you divide 120 by 16, you're going to get a rounded 8, basically, right? And then here's our epoch, right? We're currently on the 3rd, now the 4th.
That's so cool.
Show you all the tricks.
Okay. And then I'm gonna start writing here we're importing pandas, which lets us graph our results. So we're going to run this, and this helps us plot our accuracies in a sort of graph. Yeah, if nothing interesting pops up, you have to run it again, and then yeah, we have a straight line.
So what does a straight line mean?
Yeah, what does a straight line mean?
Yeah, it's not improving.
Yeah, our accuracy is staying around this 56th percentile range, and it isn't really changing. What that means is our model kind of sucks.
Yeah, any ideas on why our model is not learning anything right now?
Number of epoch, maybe?
Yeah,
We could
be.
increase that.
Could be number of epochs. What else?
Data size?
Correct. Yeah, data sets. How many images do we have?
150.
Yeah,
20.
120 for our training set. That's really small. How
That's pretty
many
small.
images do neural networks typically train on?
4,000.
Yeah, thousands. Right. So 120 is really small.
I didn't have that much time to take Chihuahua pictures from Google, okay? I had to make do with what I got.
So for the number of images that we have, AlexNet is actually not strong enough to learn anything on this data. But if we switch it to a more complex model like ResNet, you'll start seeing accuracies in the 99%.
Yeah. So here, you don't have to type anything, actually. We've already done the work for you. This will help. This will be able display our results in a more human readable format. You just have to run this code. So just Shift Enter. Okay.
Take a little bit. And go back, I think.
Yeah, it's done.
Oh, it's done.
Yeah. This one shouldn't take too long. Okay. And then we have to call the function that we've defined for you. Visualize results. Data. Validation. Okay, so we're passing in our testing set, the 30 images we have, our network, and then our transforms, and then we're gonna run this. There's our accuracy, and look at that. So as you can see, our machine is kind of split 50-50 on whether this is a Chihuahua or a muffin, right?
Pretty difficult problem.
It's a difficult problem, as you can see, yes. Very difficult. I mean, I think this sort of looks like a muffin, right? If you just focus on the head. And let's see, any Chihuahua-looking muffins down here? I think this one, right? This one could be seen as the eyes, and this one could be seen as the mouth, or the nose, right?
Oh, true.
Yeah. So, yeah, as you can see, it's pretty difficult for our classifier to really pick this up. And here are pictures I got of an actual Chihuahua. And my cousin has a Chihuahua named Cashew. And as you can see, it's still 50-50, right? Even this one.
Cool. Yeah, so we challenge you guys to do better because clearly it's not learning anything, right? But turns out that the PyTorch docs are quite legible, quite readable. So we challenge you to go look at those docs. We gave you a hint already. You can change the model to a more advanced model so that it would do better, something like ResNet. And then come back next week, show us that you were able to train it higher, and then we'll award a prize to the person who is able to the people who are able to get 99% or so.
Yes. Any questions? Everyone successfully get through everything. Okay,
Congratulations,
cool.
you
Good
made
job.
it through your first neural network.
First project. Great.
And it is 12:30, so our meeting is officially ended, but we'll stick around for questions that anyone might have. And we hope to see you next time. Next time, we're going to talk about the math in the neural networks. Thanks for coming. Same time, yeah, Thursdays, 11 a.m., 12:30 p.m. is when we.
Thank you guys.
Oh, and thanks for coming, Gilbert. See you next time.